Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. Practice problem 6, determination of compass error by azimuth of the sun. Here we go. Problem 6. Let's record that first. Problem 6. And we have a bunch of givens in the problem. Givens. Our givens are the date. The date is given, and it is February 9th, and that's 1981. And the zone time is given, 7:39. Zone time equals to 7:39. And the DR position is given. DR position is given, and it's latitude 23 degrees, 31.0 north, 31.0 minutes north, and the longitude is part of that. And it's 143 degrees, 143 degrees and 41.0 minutes east. 41.0 minutes east. And now it gives us, at that time you observe the sun's bearing. So the sun bearing is equal to 104.5 degrees PSC. And the chronometer reads 9:37:12. So the chron time is equal to 9 hours 37 minutes, 9 hours 37 minutes and 12 seconds. And then the chron error is given. Chron error is equal to 1 minute 52 slow, 1 minute 52 seconds, and that is slow, so we add it. And the variation is also given. Variation is equal to 3.5 west, 3.5 degrees west. And then the question, what it's getting at is deviation. It asks, what is the deviation? So our first step is to get the approximate GMT, or Greenwich Mean Time. So let's get the approximate GMT, and that will given by, take the zone time. So we take the zone time, which is equal to 7:39, and then we take the longitude, which is 143. Say 143 degrees, 41.0 minutes east. We're going to divide the 143 by 15. If we need to account for this 41 minutes, like if it's close, we will, but usually it's not. Usually we don't need them at all. So 143 divided by 15 equals, 9.5. So we round up. If we would have counted for the minutes, it just would have made it more apparent that we round up. So this is equal to 9.5. So it's equal to 9.5, which means we round up to a whole number, 10 hours. And now how do we know if we add or subtract this from the zone time? Well, it's the east right here. So if we were to look at a graph, We just kind of graph this out. These are the time zones. And this is the prime meridian, which is at 0. It's Greenwich Mean Time. If we go to the east, we are adding to the east. If we go to the west, we are subtracting to the west. So you could think of it like from New York to California, you subtract, and vice versa. So if we're in the east and we need to get back, we need to do the opposite. We need to subtract to get back. So we need to subtract 10 hours from our zone time, which this is already interesting. Look at this. If we subtract 10 hours from our zone time, we're going into the previous day, aren't we? And to do this math, we just add 24 hours to 7. So say 24 plus 7 equals minus 10 equals 21. 21 hours and 39 minutes. So 21:39. This is our approximate GMT, which is on, now it's February 8th, right? It was Feb 9, and now it's Feb 8th. Okay, so this is our approximate GMT. We know about where we are. Let's find our actual GMT. This is basically checking what day we're in, which came in handy, right? Actual GMT. The cron time, 9:37:12. So cron time is equal to 9:37:12 seconds. The cron error is 1 minute 52 seconds. 1:52 seconds, and it is slow, so we add it. We're going to add it. All right. 2 and 2 is 4. That's 64 seconds. We're going to have to account for that. 37 plus 1 is 38 minutes. So we have 9 hours, 38 minutes, 64 seconds. But this 64, there's 60 seconds in a minute. We need to put one over here. So we end up with 9 hours, 39 minutes, and 4 seconds. And now, this is interesting, right? So our approximate GMT and our GMT, these are 9 hours off. This chronometer has ambiguity. The way you check it is you add 12 hours. If you add 12 hours to it, what do you get? 9 plus 12 is 21. 21 hours, 39 minutes, and 4 seconds. This is what we're working with, right? And this is February 8th, not 9th. And this is 1981. Okay, cool. So now we have our GMT. This is our GMT, which allows us to look up the GHAs. Good. We got our GMT. We cross-checked it with our approximate GMT. We come back over here and let's get the GHA, the Greenwich hour angle of first 21 hours. 21 hours, and then we'll get the GHA of the increments, which is 39 minutes 4 seconds. 39 minutes 4 seconds. So those are going to equal some values. And then we're going to find the declination too, because we'll set up the declination and we'll get the D value because this information is on the same page as these. So let's get our GHA for 21 hours. Nautical Almanac. We need to get to the day, which is February 8th. May, April, March, February 9, February 8th. So February 8th, sun 6, 7, February 8th of the sun. We're looking for 21 hours way down here. Okay. February 8th, sun 21. So 13126.2. 13126.2. 13126.2 minutes, degrees, and the declination's right next to it. So again, February 8th, 21, the declination's here. See that south 14 comes down. South 14, 48.4. South 14, 48.4. South 14, 48.4. South 14, 48.4. Okay. So we're back over here. South 14, 48.4. Now we need a D correction. It's 0.8. D is 0.8, right? But if you look, it's decreasing. We need to know whether we add it or subtract it. 48.4, 47, 46. We subtract this D value. So D minus 0.8. Minus 0.8. Now we have these values. We can go into the increments and corrections table all the way at the back. For 39 minutes, we're looking at 47, 35, 39 minutes and 4 seconds. Here we are. So 39 minutes, and then here's the seconds. 39 minutes, 4 seconds. Yeah. 9 degrees, 46.0. 9 degrees, 46.0. 9 degrees, 46.0 minutes. 9 degrees, 46.0. See, 39 and 4, 9 degrees, 46.0. It's worth double checking this stuff. If you mess it up, you just kind of got to start over. Okay, and our D correction is 0.8. Here's the D correction, 0.8 right here. 0.5 is what we use. So minus 0.5. So we're thinking minus 0.5. So 48.4. 48.4 minus 0.5 equals 47.9. 47.9. So it's south 14, declination equals south 14, 47.9. Let's add these. So point, that's 2. 6 and 6 is 2. 1, that's 3, that's 72.2. 140. And then I'm just going to, there can only be 60 here, right? Let's take one over. So if we take 60 out of here, we get 141 degrees. And then this is 12.2. And this is the GHA of the sun. Greenwich hour angle sun is equal to this. And now what we need is we have an east longitude. We need to add our east longitude. So add our east longitude. If our longitude was west, we'd subtract it. But our longitude is east, and it's 143, 41.0, 41.0 minutes. Let's add this. 2 plus 0 is 2. 2 plus 1 is 3. That's 53.2 minutes. Let's add this. 1 and 3 is 4. That's 8. 284. 53.2. This is our LHA, our local hour angle of the sun. Okay, now that we have these, we can start to make our table. So let's make our table. We'll start over here. We'll say declination we need. We need the D, R, lat, and we need the L, H, A of the sun. What do these equal? Our declination is south 14 and 47.9. 47.9 minutes. Our DR lat, 23 degrees, 31.0 minutes north. And then our LHA is 284 degrees, 53.2 minutes. 53.2 minutes. Okay. Now, are these the same or contrary? Our declination and our DR lat? DR lat's north, declination south, that's contrary. So we could say our dec and DR lat are contrary to each other. Good, we're going to need that. Now let's get our base. They call it a base argument. Base argument is that the base are the degrees. So 14 degrees, 23 degrees, and 284 degrees. 284 degrees. And that can get us our base angle, or Z, base Z, from the site reduction tables. So let's check out our site reduction tables. We're looking for, okay, see the first half of the book, the latitudes only go to 22. So we're going to be in the last half of the book. And we need an LHA of 284, contrary. So there's 3, 2, 92, 86, 85, 84. 284, contrary. So we're on this side. The other page is same. See that? Same. Contrary, 284, 23, 14. So here we go. We are contrary, 284, 23, 14. And here's the Z column, 108.5. 108.5. And just to double check, contrary, 284, 23, 14. 108.5 right there. 108.5 is our base. 108.5, and it goes in all three of these. Now we have to tabulate the Z. Tabulate Z. And to do that, we're going to take 14 and we'll bump it up by 1. So it'll be 15, 23, 284. And then we bump the DR lat up by 1. So it's 14, 24, 284. And then lastly, we bump our LHA up by 1. So it's 14, 23, 285. And the answers go here. So here we go. Let's bump this deck up by 1. So it would be 15, right? Declination, yeah, bumped up by 1 be 15. So we're contrary, 284, 23, 15, 109.4. 109.4. And now bump this 23 up by 1. So it's 24. So now we're 14. Okay, so we're contrary, 284, 24, 14, right here. 108.6. 108.6. And now we need to bump our LHA up by 1, so it means we need to turn the page. Yeah. And so now we're over here. And we are 285. Contrary, 2314 Z column, 108.9. 108.9. Okay, now we need to find the difference in the angles. The difference in Z. So I can see this one's bigger. If the tabulated, just go tabulated minus base. So this one's going to be a positive. This one's a positive. And also, they're all positive. Okay. Let's crunch some numbers. 109.4 minus 108.5 equals 0.9. 0.9. And now the next one, 108.6 minus 108.5. 0.1. 0.1. One more time, it's going to be 0.4, but I'm just going to put it in anyways. 108.9 minus 108.5 equals 0.4. Okay, now we need the increments. And the increments are these, all these minutes. 47.9, 47.9, 31.0, and 53.2. Okay, and now we can calculate the correction. The correction is equal to the difference times the increments divided by 60. Let's check these out. So difference times increments divided by 60. So the difference, 0.9 times the increments, 47.9. 47.9 equals divided by 60 equals 0.72. 0.72. Next one. 0.1 times 31 equals divided by 60 equals 0.05. And the next one. 0.4 times 53.2, 53.2 equals divided by 60 equals 0.35. 0.35. And now we can find the total correction, which is equal to the sum of all these. 0.72 plus 0.05 plus 0.35 equals 1.12. 1.12. We're just going to go to the 1 decimal point. So here's the total correction. Now we can use this to correct the base angle. So the base angle, or base Z, is equal to 108.5. 108.5. And the correction is a positive 1.12. So plus 1.1. This is going to give us our angle in quadrantal notation. 6, we added 8, 9. 109.6. This is our Z, but it's in quadrantal notation, so we need to label it north, south, and east, west. So north, we go by our DR lat to name it north. And then we go by the LHA to name it east or west. So LHA is greater than 180, so we name it east. Good. So our ZN, so that's our Z, and our ZN is angle from north. So let's draw this out. Okay, here's our little graph. North, south, east, west. Okay, so we're north first. We're from the north, so we're up here. And now we're east. And 109, so we're past 90. We're somewhere down here, right? So this is our Z. But if you look from north, our Z is actually equal to our ZN in this case. So that's good. Z is equal to Zn. So Zn is just equal to Z, which is equal to 109.6 degrees true. Let's correct our compass and say TVMDC, true, variation, magnetic, deviation, compass. We're going down. If we go down, we add west. So 109.6, 109.6 degrees true. Variation was given 3.5 west, 3.5 degrees west. We're going down, so we add that. 109.6 plus 3.5 equals 113.1. 113.1. And now our compass, here we are, 104.5. 104.5 degrees PSC. So we're going, it's less. So this is going to be east. So let's subtract. We got 103.1 here minus 104.5 equals 8.6 east. 8.6 degrees east. And let's check out our problem. Look at that, D, 8.6 east. So the answer to practice problem 6 for determination of compass error by azimuth of the sun is D, 8.6 degrees east.